Hello, Algebra 2, and welcome to Lesson 6.1. We're going to talk about key features of exponential functions. Our essential question today is how do graphs and equations reveal key features of exponential growth and decay functions? Well, let's get that question answered. Let's get right into it and look at example number 2 where we're going to start. We're going to look at graphs of transformations of exponential functions. So we're going to graph this function. And then we're going to look at the parent function, 3 to the x. We're going to talk about asymptotes. We're going to talk about some important features of this graph as well. All right, so whenever I'm graphing something, I like to go to my calculator first and then start graphing some points as well. So let's go ahead and get out that calculator. And we're going to graph 3 to the x power. So this is 3 raised to the x power. Graph. And what we're going to notice about this is that there is an asymptote here. This asymptote actually happens to be the x-axis, which is the line y equals 0. So this graph, for very, very large negative values of x, right, is going to get as close as you can imagine. Our y values will get as close as you can imagine to 0, but will never, ever, ever actually reach 0, right? So also let's talk about domain and range of this thing, right? For our domain, we'll see that, right, so for all of our possible x values, it looks like x could be any value, right? As this thing goes out this way, right, it just keeps growing up. And as this thing goes out in the negative direction, we said that it gets really, really close. Our y values get really, really close to 0, but x just keeps going. So then that means that our domain is all real numbers or contained in the interval from negative infinity to infinity. Let's talk about the range of this function real quick. So our possible y values, well, we know that y cannot be 0 or less than 0, right? We can see that from the graph, but it looks like our y values can go all the way up to infinity. And so there's our domain and range. Now we got off on a little side tangent. The question was asking us to graph this and then compare it to the graph of y equals, or f of x equals negative 3 to the x power. So let's do that as well. Let's look at that. Let's make a comparison there. So we're going to graph that one. If we're looking back at what the question was actually asking us, there we go. We're going to graph this one, and we're going to compare. We also have an intercept. I did forget to talk about that one. Let's talk about that here in just a moment. Let's go ahead and put in that negative. Make sure you're using the negative, not the minus sign. 3 to the x power. So we're going to graph them both, and we'll notice that that negative sign caused a reflection about the x-axis. So what changed in this? What is the difference? Well, here we have a y-intercept at 0, 1, and this one changed our y-intercepts to 0, negative 1. Awesome. Cool. Our domain is going to stay the same of our red function. That's negative 3 to the x power. But the range is going to be switched, right? On the low side, we'll go all the way down to negative infinity, but it's going to stop at 0. All right. What if I had to graph this thing by hand? Well, I would go ahead and make a table of values, and I would plot those values, right? So imagine I wanted to graph f of x equals 3 to the x power, but I have no graphing calculator, right? So I'm going to choose some values of x and see what my y values are going to be. I like to try some negative values and some positive values around 0. So if I plug -2 right in there, we wind up with something interesting, right? That's f of -2 is 3 to the -2 power. Remember our rule that said that if we have some a to the -m, that's equal to 1 over a to the m. So that's the same thing as 1 over 3 squared, or 1/9. That's pretty small value. So you can see that that is getting kind of close to 0. What happens when we plug in the -1? We wind up with 1/3 for the same reason that I stated earlier. 3 to the 0 power is 1. That's that y-intercept. 3 to the second power is 9. I don't know why I put the 2 in. It's kind of weird. I'm going to fix that. Let's put the 1 in here. And 3 to the first power is 3, and then 3 to the third power is 9. And that's where you start to see that exponential growth right here, right? This is going to start to, these values are going to start to increase really, really quickly. All I would do to graph that is just plot those points, and then I know how it's going to look because I know what exponential functions look like, and I would go on in that way. All right, let's do another one. Oof, it's going to leave all my stuff there. Let's do another. What is going to happen here? All right, so we've got the 3 to the x power on our graphing calculator. Let's get rid of this -1. I'll just hit delete. Sorry, all this stuff is there. And this was 3 to the x power minus 4 is the next thing we're doing to compare. Hit graph. And probably just as you suspected, right, you're going to have the same graph translated down for units. What happens? Our y-intercept is going to be translated down 4 units, and the domain and range is going to change. Or sorry, the domain is going to stay the same. The range is going to change in the same way, shifted down 4 units. All right. Let's move on to something else. All right, so commonly, exponential models are very common, and they're very useful as well. In this case, we have a population growth. So what we're going to do is we're going to write an equation function to represent this particular situation. You need some information up front to make this happen, and that is, I mean, how in the world do you do this? So for exponential growth, we call this e of x. We'll say a times 1 plus b to the x power. And we'll talk about what each of these things are. So this a that's out in front is our initial population. If we're dealing with population growth model, b is our rate that it grows at, and x is going to be how long. It's going to be some sort of time. Okay, so how long? All right, let's go ahead and use this model to create a function for this situation. So what was our initial population? Our initial population is 4.6 million. So I'm going to just put 4.6, and we'll change our answer in the end if we're going to plug something in, right, where we'll express that in millions, our answer. All right. The 1 is going to go in there. What was our rate? 1.3%. We must express this as a decimal. Okay. Moving the decimal point to the left 2 places. And then x. We don't know what it is. We're just making this model. So what this does is if I plug in some value of x, right, it will output some expected population in that case. All right. So next we're being asked, what happens, what will the population be in 2040? So in 2010, it was 4.6 million, my bad, I don't know why I all of a sudden thought billion, no cities are that large. I don't think. No city is that large. So essentially what we're being asked for is to let x equal 30, right? Since 30 years have passed between 2010 and 2040. So essentially, we're being asked, what is e of 30? To be able to spit out some number here. I'm going to go ahead and add these two together right away because it's really easy to do. And then we'll plug in the 30 up here. Okay, well, now we need to remember, please follow your order of operations. Remember, exponents have got to go first. A really common mistake is people try to multiply this 4.6 right away. Don't do it. Don't do it. And then I just messed up by doing that. All right. I'm just going to rewrite this since I wound up, gosh darn, doing that 1.01 to the 30 power. My bad. All right. So let's go ahead and raise 1.103 to the 30th power. 013. I know I said it in a weird way. All right. So just to show you that I am following my order of operations, I'll say that this is approximately 1.473. And now we'll multiply that for, and that is going to be approximately 6.777 what? Million, right? Million. Okay, fantastic. Let's keep rolling. Okay, let's make another one. Let's talk about different functions. So that particular one works for a population growth. Also, another way that you'll see these is as some f of x equals a times b to some x power as well, right? And it still stays that this is our initial. This is our rate of growth. And then this could be, this is usually time. And that's what we have here. And we're being asked if this represents exponential growth or decay. And I'm going to tell you that if b is less than 0, oh, sorry, silly me. If b is less than 1, and it always has to be either less than 1, b cannot be, it can't be less than 0. So, and it can't be equal to 0 as well. But if b is a fraction, right? If b, oh, there's a much better way to say this. I'm sorry. If b is between 0 and 1, not including either of those, right? Then the function represents exponential decay. Okay? If b is 1 or greater, right? So then it's exponential growth. If b is greater than or equal to 1, then the function represents exponential growth. Awesome. So in this case, right, we look at it and we say, hey, b is indeed between 0 and 1. It's a fraction or decimal. So that means that it's gonna represent exponential decay. Let's look at another one. So what is the rate of decay? 0.08. Sorry, I don't know why I keep doing that. But 0.8, 0.8 is what I really need to say. Just opening random things for fun. So for exponential decay, remember we're talking about this model for where we have b, in this case with decay, b is equal to 1 minus our rate. So to find out our rate of decay, we would look at 0.8 is going to be like 1 minus this rate, right? So we'll subtract 1 from both sides. And that's going to give us a negative 0.2, right? Is negative r. We'll change the sign of both sides and we find out that our rate of decay is 0.2. Rate of decay is 0.2. What does that mean in the case of this function, in the case of this situation, right? In context, what does it mean? It means that a car's value decreases by 20%. And I'll just write that down. And we're saying that's happening each year. Awesome. All right, let's do another one. All right, so let's go ahead and get out our graphing calculator to graph this thing. And over a reasonable domain, let's talk about what that means. Is the years since purchase ever going to be negative? Absolutely not, right? Is the price of the car ever going to be negative? Definitely not, right? Then I think we'd want to look at it from maybe 0 to 10, and we won't need to look at any y values less than 0 as well. Let's see how we could do that using our calculator. All right, let's get rid of these things real quick. And then let's go ahead and graph what we have. It is y equals 24 times 0.8 to the x power. 24 times 0.8 raised to the x power. And we're going to hit graph. And it's going to give us kind of just a piece of it. We're going to change our window so that we're not looking at any x values less than 0. We're not going to look at any, yeah, I like going up to 10, right? That's 10 years. Let's not look at any y values, right, less than 0. And let's see if we can get a better picture of this graph. I still would like to see a little more. I'd like to be able to see that x-intercept, or sorry, that y-intercept. But the y-intercept is going to be at 24, right? So let's see. We're going to have to change our window. We would like y to go all the way. Let's have, maybe we'll look at it out to 20 years. And then we know that this has got to be at least 24. And there we go. That's a much better look at this graph, right? And then I think we're asked some specific questions about this. We're asked, what do the y-intercept and asymptote represent? And when will the value of the car be about $5,000? All right. So from our graph, our y-intercept, right, that represents the starting value, right? So at year 0, the value is 24,000, I believe our units are, right? In thousands. I believe it's dollars. Yes. Perfect. All right. Okay, around when will the value be about 5,000? So we're looking at, right, what value we have here. And interestingly enough, like we could plug that into the original function, but since we're sitting here with a calculator, let's use our trace, right? When will the value, so we would like a y value of 5. It said about when. So we would say at about 7 years. At about 7 years, we're going to have a value of $5,000 for this car. Awesome. Okay, I think that we have one extra to look at as well. All right, so what's the rate of growth or decay? So this one will be decay, right? And so our rate will be so we'll have b, right? Remember, b is going to be equal to 1 minus r. So 0.75 equals 1 minus r. If we do the math, we find that r is going to be 0.25. All right. And that was it, just another way of looking for that. Hey guys, thank you so much for watching today. Look out for your assignment that goes along with this particular lesson. Hey, I hope you're having a fantastic day. And if it's not, gosh, I hope it's at least interesting. Learn something else today. Bye, guys.